Guten Abend allseits, Guten Abend Indian, Guten Abend Deutschland. Good evening everybody, good evening India and good evening Germany. We are really obliged that Mr. Avinash Chaturvedi, today's speaker, is joining us directly from European Southern Observatory, Garching Ludwig Maximilian University, Munich, Germany. Wir sind sehr dankbar, dass Avinash Chaturvedi ji aus Ludwig Maximilian Universität Munich, Deutschland beigetreten ist. Herzlich willkommen aus Indien, Mr. Chaturvedi. We extend a very warm welcome to you from India. I welcome you all on behalf of Sky Foundation. I welcome you all on behalf of the VIPNet Club, all the VIPNet Clubs, Ignited Minds VIPNet Club, today's organizer, Sky Amateur Astronomers Club. I welcome you all again on behalf of Women-led Science Club and also our chief patron, Indira Gandhi Planetarium and UP Amateur Astronomers Club. Today, as we all know, we have gathered here for the 5th episode of Astronomy Delight series that our collaborative efforts is presenting. And yes, I have forgotten the EduSTEM Initiative Global, which is really collaborating us directly from US with its representatives, with its speakers, and with its manpower day to day. So kindly forgive me because I have forgotten the EduSTEM Initiative. So I welcome you all on behalf of EduSTEM Initiative Global as well. So as I was talking to you that today we are here on the 5th day of the Astronomy Delight series, or in fact the 5th episode, and today's talk or the perspective of today's talk is quite a unique in its own kind, because we will be concentrating, as we all know, we are celebrating the Heritage Astronomy Week since 2nd of May. So we are on the 4th day on trot with speakers, and today's theme actually is the Nobel Prize of 2019. The Nobel Prize of 2019 in physics was awarded, as we all know, to 3 of the astrophysicists for their contributions to the understanding of the evolution of universe and the Earth's place in the cosmos. One half of the prize, as we all know, went to James Peebles for the theoretical discoveries in the physical cosmology, and the other half was given to Michel and Didier Queloz for the discovery of the exoplanets of orbiting a solar type of a star. So in today's journey, we will be taken up to a journey of cosmology, a journey of time in universe by an esteemed speaker, Shri Avinash Chaturvedi ji. So let me introduce to you all Mr. Avinash Chaturvedi ji. Avinash Chaturvedi ji, as you all know, is joining us directly from European Southern Observatory, Germany. He is a PhD scholar there at Ludwig Maximilian University, Munich, Germany, with his thesis on a dynamical mass mapping of Fornax galaxy cluster. He is actually an Indian by heart, an Indian by residence, an aborigine of Lucknow. With its, he has got a par excellence career ever since his early days. Awarded with Amul Vidyashri Award for outstanding academic performance in high school in class 10th of India by Amul Sagar of Gujarat, India. Thereafter, he excelled in the Namaste Erasmus Mundus scholarship under Master Exchange program, and he went on forward again with the Amidex grant for studying astrophysics at Aix-Marseille University, France, and right now he has been a winner of International Max Planck Research Scholarship, IMPRS, as we all know, on astrophysics, and he is currently a research scholar in Munich, Germany. So he has been not only a research scholar, but his publications has also been widely regarded as far as his contributions to the field of astronomy and astrophysics are concerned. And we are very much esteemed to have him on board today, because we have already seen his research papers titled How Robust Are the Estimates of the Local Dark Matter Density. An astrophysicist by heart, an Indian by heart, he has been a student member of Indian Science Congress ever since his early days, and has helped Indira Gandhi Planetarium, Lucknow, and Council of Science and Technology, Uttar Pradesh, in the installation of the refraction telescopes in his early study days when he was here a student at Lucknow. A violinist like Einstein, expert in playing flute, sketching, and painting, He is a man who has donned many hats. So without wasting any time, I am just calling on board our esteemed speaker for the day, Avinash Chaturvedi ji, to kindly grace the platform of Sky Foundation, Vigyan Prasar, the collaborating Ignited Minds, SkyAC, and women-led science WIPNet clubs, and spread in the minds of the audiences who have joined, traversing north to south, east to west, and even the oceans, with the delight of the cosmos in the series of Astronomy Delights. So over to you, Chaturvedi ji. Welcome you, welcome you, welcome you.
Thanks a lot, Amritansu. I hope that people can hear me. And first of all, let me check that whether you can see my full screen or not. So at the moment, I think you can see it half, but now I guess you can see it completely, like the full whole screen on the PPT on the complete screen.
I would like to request the audience. You can see Avinash Chaturvedi ji is having two different icons. From one, you can see his face, and from the second, where there is an arrow, you kindly pin it up, and then only you will be able to see the real presentation, and you will be able to enjoy the gist of the talk. So kindly do not interfere in between when Avinash ji is talking. Over to you, Avinash ji.
Yeah, thank you. Thanks a lot to Amritansu. Really, I'm grateful that you made such nice words about me and said to everyone. Well, but let me clear that I'm just a student like you all, and not a very good astrophysicist. Like it's really a quite big term, and to be astrophysicist, it's a hard thing, and I'm on a track of beginning, starting thing. So, and just a student like you all. So thanks to Sumit Bhaiya for contacting me and for having me here, to all of you for giving me an opportunity to talk about this work, like about the Nobel Prize in Physics for the last year. And I decided to talk about this work in Nobel Prize in Physics for the year 2019. It's like in physics, but mainly it's given to the astrophysicists for their work. And thanks to everyone who is listening me. So as you can see, the first thing or the title of my talk is Nobel Prize in Physics 2019, but there is something else written at fundamental. And just let me know, can you see my mouse point too? I guess you can see. Okay, so
Yes, sir,
as
you
you
can
can
see.
see, that I have written fundamental answers about our existence. So the Nobel laureates of last year in physics has helped us in understanding the fundamental questions about our universe, about our existence. The questions like how did our universe begin, how it has evolved, and how unique is our place in the cosmos. These kind of things were explored by the Nobel laureates of last year, and the award was given to the James Peebles. It was shared half by the James Peebles for his theoretical discovery in the physical cosmology, and the other half of the award was given to the Michel and Didier Queloz for his discovery of an exoplanet orbiting a sun type of a star. And before I present their work, I would like to just very briefly talk in just one slide what is Nobel Prize. So let's get started, and then I will keep on continuing about talk about briefly about our cosmos, and then go deeply in their work, and then finally present that how these people have helped us in exploring these fundamental things. So let's get started. Very simple slide about Nobel Prize. And the Nobel Prize, like it started in 1905. The first prize were given in that time. And basically it came like Alfred Nobel, who's a Swedish inventor, engineer, businessman. He drafted in his will that 5 prizes should be given to the people or the group of people who has really contributed for the benefit of the humanity, like outstanding contribution for the humanity. Initially, it was just 5 awards, but later one award was more added in the category of economics. So there are 6 categories at the moment: physics, chemistry, literature, psychology, peace, and finally economics. And here you see the Alfred Nobel and just logo or the medal, the front picture of the medal for the Nobel Prize. So in summary, this prize is given for the outstanding contribution to the individuals or the group of peoples, mainly 3 people, but if you go for the Peace Prize, then it can be given to a group of people for their best contribution or the best benefit for the humanity. So this was about the Nobel Prize, but let's come back to our topic where I was talking about the Nobel Prize in Physics for the last year. And before I talk about the Nobel Prize in Physics for last year, I would like to talk very briefly about our cosmos and how it is related with the work of the Nobel laureates of the last year. So here, what you see is the picture of our cosmos taken from Hubble Space Telescope. And here, you see a variety of different objects like galaxies, some of them are stars, and this one is a deep image taken from the Hubble Space Telescope up in the sky. So if you go back 100 years in time, then astronomers, like particularly Edwin Hubble, has observed these kind of objects, galaxies. And what he noticed that these objects were moving away from us. They were growing. There was a kind of expansion. So they noticed that since these objects were moving away from us, so if you go back in time, then these objects were held together closer and they were very near to each of them. So basically, what we see universe as today is not the same as yesterday, and it will be not the same tomorrow. So every day the universe has keep on changing, but since these objects are growing, they are moving apart from each other. So if we go back in time, then there must be a phase, there must be an initial moment when all these objects were held together. And this led to the formulation of the beginning of the universe, which we called as the Big Bang. So Big Bang is a hot and dense initial phase of the universe where all the objects were held together, they were close, but as the time passed away, these objects started moving, the objects got separated, they started expanding, and the gravity plays its role. And different kind of objects like galaxies or the stars, or even the objects which we see daily like the stars, sun or moon, or even home planet Earth came into existence. So this was kind of about the beginning of our universe and how might have these objects, massive structures might have came into existence. So if you like to summarize what I have said about the beginning and about the evolution and about our Earth, place, and cosmos, then you can do it in a picture like this. So at the very moment, we have a hot and dense phase of the universe called Big Bang. And then there is evolutionary phase of the universe, which is roughly like a period of 14 billion years, during which different type of objects came into existence. And then finally, we have our home planet Earth. So this two part, the beginning and the evolution, was explained by James Peebles for his lifetime work, and our Earth, place, in cosmos was explored by other two Nobel laureates, which are Michel and Didier. And now I will talk about how James Peebles' work has helped us in understanding like why Big Bang might have happened in past and what are maybe the physical regions that how these objects might have originated. And then finally, I will go on for talking about how unique is our Earth in the cosmos, taking the work of Michel and Didier. So let's start from the work of the James Peebles. Let's start from the basic, very beginning. So starting from the work of James Peebles. So here, you see a cartoon picture. I just designed it just to explain that what might be a case of Big Bang, just to explain it to a very basic level. So here, try to imagine that these red circles and the yellow circles are the teeny tiny particles. And these white foggy light is just the light which we see near around us. So these kind of different teeny tiny particles and these light particles, imagine that this is kind of soup, all mixed up together. And this is mainly the initial moment, and this phase of the universe was really hot and dense. It was so hot and dense that even the light particles, which travel with the speed of light, we all know, and couldn't escape from this dense condition. But as the time passed away, these teeny tiny particles started combining. Like the gravity plays a role, and they started combining, and they lead to formation of the fundamental elements. At this moment, the photons or the light particles were free, like the universe state was a little bit less denser related to their initial state. And at this time, the light particles were free to escape. And this was the first glow of the universe, and that's why I call this as the first light. This is like when we see something, we know that there is something existing. So this was the first moment representing that there might be an initial condition of universe, and at this moment, the first light escaped. And then in the theoretical term or in the scientific term, we call this as the cosmic microwave background radiation. And James Peebles, in the year 1965, here you see a picture of James Peebles, he made important theoretical contribution in understanding that if something like Big Bang has happened in the past, and if the objects are moving away from us, then there must be a first law of the universe. Like he made the contribution by theoretical calculation, and he called this, like people call this as cosmic microwave background radiation in the science term. And here, like, is the cartoon image representing that how might be first light have originated. And here in the elliptical form, you see a real scientific picture of the cosmic microwave background radiation. So he did the calculation in 1965, and later Penzias and Wilson, here it's showing their picture in 1965. They also detected this, they by chance they detected this, the presence of this first light, and actually these people contacted James Peebles to confirm that what they are detecting. And later in the year 1978, they Penzias and Wilson got Nobel Prize for the discovery for detecting the first light or the cosmic microwave background radiation. So you see, like James Peebles already made the theoretical calculation, but he missed the Nobel Prize, and it went to the Penzias and Wilson in 1978. But it's okay, it's fine. In future, in the coming slides, we will see that he missed the Nobel Prize and again. But this was his first important contribution. And let me tell you that James Peebles got the Nobel Prize for his lifetime contribution. So he did a lot of work, but I will be talking just only two important contributions. The first one is cosmic microwave background radiation. And later, in the year 1966, he used the idea of the first light or the cosmic microwave background radiation to predict, and he calculated that how much matter or how much mass should have been created after the Big Bang, like how much hydrogen or helium might have formed after the Big Bang, just using the idea of the CMB or cosmic microwave background radiation. So this was about the beginning of our universe, and also since Penzias and Wilson detected microwave background radiation, so it gave an important support that something like Big Bang has happened in the past. So this was a concrete support that something like Big Bang has really happened in the past. And so this was about the beginning of our universe, that it started from an initial hot and dense phase. But now let's come to a point about our evolution of the universe. So I have a very simple question to all, and since it's not an interactive talk, so I guess I will not be getting responses from all the people, but I have a very simple questions, and even if someone will say yes or no, I will be happy. That here you see a picture, just a black picture, and I have a simple question then. Do we see our night sky like this? I hope someone can say yes or no. Yeah. So okay, that's a good response. But I know that our universe, our night sky doesn't look like this, because even if you go outside, then you can see stars. On a clear night sky, you can see many stars. If you use a telescope, you can see galaxies. So clearly, it's not a blank sky like this. So we knew that there are other objects beyond our sun, or more more than our home planet or the moon. There is other kind of objects existing nearby us. So how these objects have came into existence? First, I talked about the beginning, and now coming about how these objects might have been originated. So here, James Peebles came again in the game, and he made important contribution, giving idea about how these objects might have been evolved, or might have came into existence. He used the idea of the first light. So he said that the first glow of the light it gets spreads. And he saw that if there is a little inhomogeneities, little differences, imagine that my 5 fingers are going and some of them are together and some of them are farther away. So these differences, as these light have spread, because of little differences, how they have spread in the universe, they can go further and further, and they can become a larger clump of matter. And this led to the formation of the galaxies or the massive structures which we see in our universe. He made this calculation. He saw that this might be a region for objects existing like galaxies or massive structures in 1980s. And this mainly came from his little idea, little but important idea, that the first glow of light is not homogeneous, like it's not everywhere kind of same. There is little differences, very teeny and tiny differences, which grew further and further, which led to the formation of the massive structures like galaxies. And this thing was detected by in the year, like this was later detected by Kobe satellite. And for this detection, or for this theoretical discovery by John C. Mather and George F. Smoot, that the first glow of the light, which is CMB, is not very smooth, they detected this kind of inhomogeneities in the first light, and they got the Nobel Prize in 2006. So later, he missed the first prize. He missed the first Nobel Prize for his theoretical calculation in 1965, and later, what he calculated in 1980 about the formation of the massive structures, he missed the Nobel Prize again, and he got other people, John C. Mather and George F. Smoot, got the Nobel Prize for this little inhomogeneities, for discovering the little differences in the first light. But finally, this year, he got the Nobel Prize for his theoretical lifetime achievement work for starting from the Big Bang and the evolution. Finally, the Nobel Committee, I will say that he was already having a much important contribution in the cosmology and the astrophysics, but having a Nobel recognition is also matters. And finally, it was recognized by the Nobel Committee. And then this was a kind of history about the Big Bang and evolution. And then this teeny slice of matter, which forms the galaxies and massive structures, is also responsible for the formation of our home planet Earth, or the objects which we see nearby us, like moon or the sun. And this other part um, of the existence was explored by Michel and Didier Queloz about specifically how unique is our place, in the universe, like how unique is our Earth in the cosmos. Here you just see a beautiful picture of our solar system and a picture of Michel and Didier Queloz. The fundamental questions like, are we alone in this universe? With the alone, I mean at the first time, like, let's not talk about the life, but let's talk about, are there other planets around any other stars? So if there is a planet around another star, we call this an exoplanet. So are there any other planets? Then there might be a chance of life on those planets too. So the question comes that if there is a life on other planet, then the first question comes that we have to detect planets. How unique is our Earth? Are there other planets similar to kind of Earth in a nearby other stars too? This part was explored by Michel and Didier Queloz. And before I present their work about how they discovered a planet around any other star, rather than instead of our own sun, like an exoplanet, I would like to very briefly talk about a method, a simple method, that how people can detect a planet around any other stars. But it's always that the solutions starts from the problems. What might be the biggest problem in detecting a planet? So let's try to understand what might be the problem. So here you see an image of the sun. And if you look carefully, then you can see a black dot here. Actually, it's Mercury as seen from our Earth. It's transiting and we see it. So here you see a dot kind of thing. Sun is relatively very close to us in comparison to other stars. So, and that's why we can see that even the Mercury, when it's crossing, we can see it as a black dot. But it's not possible for the other in the case of other stars, because they are actually very far away from us and they are very bright. And since planet doesn't have its own light and sun or the star is too bright, then it overshines the presence of a planet. So it's really hard to detect a planet around any other stars. But luckily, people have worked and people have developed some of the methods through which we can detect the presence of a planet around any other stars. And I will talk about a very simple method which is easy to understand to check how we can detect the presence of a planet around a star. So let's start about how we can detect a planet. So imagine that there's a star somewhere around our solar system, farther away from us. Might be there might be a planet around this star, but since it's oversigned by the presence of a star light itself, we can't detect it. But imagine that there might be a planet around it. It's revolving around it. So when there is a presence of planet and it's revolving, then the gravitational attraction between the planet and a star acts. And what does the gravitational attraction between the planet and a star does? That a star also starts kind of making a motion around the common center of gravity. For the moment, exclude the term common center of gravity, just imagine that when there is a planet around a star, then because the gravitational force of attraction between the planet and a star causes the star to make a motion. And when it makes a motion, then we see that there is a change in light which we are receiving from the star to the Earth. So let's start from this thing, that when there's an object which is moving away from us or moving away from us or coming near to us, we see that there is a change in light which we see. In the case of a star, this also happens. When the star is going away from us or is coming near to us, we see that there is a change of light. When the object moves away from us, we see that red light is coming to us. And when the object is coming near to us, we see that the blue light is coming to us. This happens also with the other stars too. If there is a planet around it, if it's revolving, then because of the gravitational interaction, when the stars moves away from us, then we see red light coming to us. And when it moves near to us, we see that the blue light is coming near to us. And if there is a kind of variation of the light coming from the star, it might signify a presence of a star, a presence of a planet around a star. And this is a simple method called radial velocity detection method of finding exoplanet around any other star. And basically, this method was used by Michel and Didier Queloz in the year 1995. And basically, they were in the observatory, the Haute province, where I was also there for just for trip for observing thing, and they still that instrument exists there in Marseille. So these were the people who discovered the first exoplanet orbiting around a sun type of a star. And when I say sun type of a star, it means like a star similar to having similar physical properties similar to our sun, like having some same temperature and same brightness and other physical properties. So they did it in 1995. But I should also mention that there were other people too before them, like in 1980s. They also kind of detected exoplanet around other stars, but they didn't claim it. So in scientific work, it's really important. When you do something, you're confident, you claim it. Because these people, I should add two important words, that these people were confident about their work and they claimed it. This was the first thing that they claimed, that yes, we have detected an exoplanet around a sun type of a star. So this kind of claiming and this kind of confidence really made them the father, I will say that the father of this new field. But other people also worked, but these people were confident and kind of very sure about their work. And after this discovery, this led to opening a new vibrant field of the exoplanet. And at the moment, we have detected more than 4,000 exoplanets. So starting from the Big Bang, evolutionary phase, the work of James Peebles, we came up to a level where we can detect exoplanets. And now with our technological advancement, we are at a level where we can detect water, the presence of water in the atmosphere of exoplanet. So starting from the beginning, we are at a level where we can detect water in the atmosphere of a planet. So this is really a massive feat, a massive advancement in the science itself, in our understanding. But still, there are fundamental things which still need further to explore by people like you all who are listening to me, and me too, that what happened, what might have happened before Big Bang. No one knows this. And we already know that there are other planets, but we don't know whether there is life there on those exoplanets or not. If there is life, then what kind of life it may be? So these are some fundamental questions, and we need these things to link all these information together. So again, I would like to say that no one, like, just from our common, it's interesting and it's curious to think about these issues from our common point of view. Like, and that's why my favorite is Einstein, who said that imagination is more important than knowledge. For thinking beyond these topics, for thinking beyond the books, we don't need no one is stopping, no one is limiting our imagination. So just from a common point of view, I would like to inspire or motivate my audience that think that what might be the cases, or if there is life somewhere, then what might be the scenario, what kind of life itself it is. So before I conclude, I would like to present a message for you all to take home, and this will be my final slide. I'm talking. That something in the very beginning was a hot and dense phase of the universe. We call this as Big Bang. And James Peebles used this idea of the first light originating from the Big Bang phase of the universe to develop our understanding that how these massive structures have came into the universe. And then finally, there are a world of exoplanets. We are not unique in this universe. With uniqueness, I mean there are other kind of planets existing around our other stars. So there are a world of exoplanets, and there is much more things to do beyond these things. And then finally, thank you to all for listening, and thanks to my colleague Forky, Henry, and Lemko for helping me in developing this talk. Thank you. Thanks to all.
Oh, thank you, Mr. Avinash, for such a wonderful lecture. Vielen Dank für Ihren Vortrag. So first, as you like, I hope like everyone enjoyed your session here. Like the Big Bang model describes the universe from its very first moments, almost 14 billion years ago, when it was extremely hot and dense. Since then, the universe has been expanding, becoming larger and colder. Barely 400,000 years after the Big Bang, the universe became transparent and light rays were able to travel through space. Even today, this ancient radiation is all around us and coded into it. Many of the universe secrets are hiding. Use these theoretical tools and calculations. James Peebles was able to interpret these traces of from the infancy of the universe and discover new physical processes. The result showed us a universe in which just 5% of its content is known. The matter which constitute stars, planets, trees, and Earth. The rest 95% is unknown dark matter and dark energy. This is mystery and a challenge to the modern physics. We get to know about the mystery of all the things behind it that you are telling. Thanks a lot for this. So as you already told us, like the 2019 Nobel Prize award was divided into two parts. Basically, the first part for the contribution to our understanding of the evolution of universe and Earth place in the cosmos, and the second part, which goes to Michel Mayor and Didier Queloz for the theoretical discoveries in physical cosmology and for the discovery of exoplanet orbiting a solar type star. Just because of you today, we get to know like how to determine, how to like examine the planet in our solar system. What is exoplanet? So also for my audience, I also want to tell them about like how the Nobel Prize came into existence. So the Nobel Prize is named after a Swedish chemist, engineer, industrialist Alfred Bernhard Nobel, who was born in 1833. He was the inventor of explosives such as dynamite, galganite, ballistite, etc. He was well aware of the misuse of explosive, but never thought that his invention will encourage war. So this was the the thinking of that noble person who took us to a journey like where we are like talking about. So thank you very much, Mr. Avinash Chaturvedi. Ich denke Ihnen alles, dass Sie heute zu uns gekommen sind. Thank you. And I also like to thank you, like our Skyak team, on the behalf of Sky Nature Astronomers Club. I would like to thank you all, and also thank to collaborate the collaborators like WLS Women Live, Lead Science Wipnet Club, the Ignited Minds Wipnet Club, and also our last but not the least, our global collaborator EduSTEM initiative. So. I hope you all enjoyed it, enjoyed the session. We have like our the presenter of this session, today's session. So if you have any question, he's ready to give you your answer. And if not, you can also write us at admin@skyfoundation.org. So let us see, like if someone has the so Mr. Avinash, we have like a question in our chat box. So he like Mohammed Tabish is asking, sir, what is the difference between astronomy, astrophysics, and cosmology?
I can say that astronomy is the study whatever is beyond our own Earth, okay, and astrophysics is kind of a more specific term dealing with the physics of the objects. Which are like in astronomy, you can include everything, celestial astronomy or the objects which we are seeing, but astrophysics is more specified to the physics of the objects, how they are formed. And if you go to the cosmology, then it deals with the larger scale, how the whole universe, like the study of the whole universe, is included in the cosmology.
Okay. There is another person in our chat box named Kshitiz Srivastav. He's asking like, do all the planets in our solar system orbit in the same plane? And if yes, then why?
No, not all the, yeah. Okay, so his question is whether all the planets revolve in the same orbit.
Let me like again recite for you. Do all the planets in our solar system orbiting in the same plane? And if yes, then why?
No, we don't see all the planets orbiting in the same plane, because like that's why we don't see transit event all the time, because all the orbits are somehow like not in the same plane. The ellipticity is different, especially in the case of Pluto and the Neptune. The orbit is totally eccentric, and so in summary, not all the planets have the same. They are not in the same plane. There might be case that maybe some of them in the same plane, but and why they are like this or why they are not in the same plane could be related to how they have formed in the what kind of planetary nebula or how they have formed. I could say I could not comment in detail in this way on this question.
Okay, and I would like to take another last question for the day, if you don't mind, sir, from our very younger participant of our group. Is this change in light happens according to Einstein's theory of relativity?
Change in light, like what I have studied is like other people can also comment on this. I know that there are other experts too, but change in light as per the spatial theory of relativity, like the frequency changes and
sorry to interrupt everyone. Actually, I asked this question when Avinash ji said that when the light goes from Earth to an exoplanet and returns back to Earth, it changes. I asked this.
No. Oh, okay, so you understand it wrong. Sorry. What I mean that if you take the example of ambulance, it's simple, the Doppler effect. When you are standing near to ambulance, just think like this. Then when it comes near to us, near to you, or near to anyone, then you get a very high frequency. Okay, and when it goes away from us, then we get a low frequency. So when the star is moving around its orbits, so we don't reflect the light. Okay, we are just at that place. When the star is moving away from us or coming near to us, we see that the light which we are receiving, there is a change in frequency or change in the wavelength. And that's when it's moved slightly away from us, then we see that there is a slight shift in the light. And this, we see that simple, you know, that the Vibgyor, like the rainbow, there are different colors. When stars moves away from us, then we see that the light moves a little bit to the redder part. And when the star moves near to us, we see that the light is moving near to the bluer part of the spectrum. It's simple like the rainbow. When the sun is down the horizon, we see the red light. When it's up, like, it's not related with that thing. I'm just explaining to imagine that how these things happen. And when the when the sun is above us, then we see that the blue light is there. So it's simple. If the star is making movement, then we see that the light is traveling to the red part and in the blue part when it's come near to us.
Okay, so thank you, Mr. Avinash. So I would like to request all the participants, if you have like other questions as well. I know there must be some curiosity going into your mind, but the time is going very fast. So we need to close our session. And I would like to request you, if you have any other questions, you can write us at admin@sky-foundation.org. We will surely revert you back. And I'm very sure that Avinash sir also able to give you answer on a mail. So do not be like worried. You will get your answer within no time. And at last but not the least, I would like to thank you, Mr. Sumit Kumar Shivastav, um, scientific officer, Indira Gandhi Planetarium. Under his patronage ship, we are able to conduct such a beautiful type of lecture session on this Heritage Astronomy Week, and it would like definitely help us a lot. Seeking to taking it to another level, we would like to announce another session for tomorrow's talk. So we will like surely update it on our Facebook page and our WhatsApp group as well. So stay tuned with us, Sky Foundation. And thank you.
Yeah, thanks a lot. Thanks a lot to everyone for organizing this and for having this opportunity. It was nice to all you have here. Thank you. Thanks a lot for listening.